let's go ahead and begin with our warm-up for today. Okay, so in these three, we've got number one here, so 5 squared over 162. Again, continuing to come back to this idea of simplifying, rewriting radicals here. So if we want to think about how can we separate 162 using multiplication so that one of the factors that we separated into is a perfect square. So if you know your perfect squares, you might think that, let's see, 162, that's 81 times 2. And the whole point of doing that is so that we can actually evaluate the perfect square part. So in this case, square root of 81 is 9. So we can evaluate that part of it. We cannot evaluate the 2 part because 2 is not a perfect square. So square root of 2 is going to stay as the square root of 2. Number 2, what is the axis of symmetry of y equals x plus 8 times x minus 6? This is factored form. If we had vertex form, it'd be a little bit easier, but we can still do it. So if we think about the graph of this, let's see, one of the x-intercepts is going to be negative 8, right, because that makes that 0. So negative 8 right here. And then positive 6 makes that 0. So we know that the axis of symmetry has to be in the middle of those two, the midpoint of those two values. So, or the average of those two values. So if we add negative 8 and positive 6, we get negative 2. So add them together and divide by 2. So add them together, you get negative 2, divide by 2, and you get negative 1. So there's our axis of symmetry right there. So at x equals negative 1. All right, number 3, describe the transformation from f of x to f, or 3 times f of x minus 2 plus 4. So we talked about transformations earlier this year, but we're going to come back to that today. So if we think about this, x minus 2, that's going to shift it. It's going to be opposite of what we might think, and we talked about why that was, but what value makes this 0? It's going to be 2. So it's going to be 2 to the right of what we normally get out when we put in 0. So it's going to shift to the right 2, and then it's going to have a multiple of 3, or a factor of 3 dilation. So it's going to stretch the graph vertically by a factor of 3. And then lastly, it's going to shift everything up 4. So those 3 components are the main ones that we're going to talk about today as well. But let's recap what we talked about earlier this year, because that's our main goal for today, is to use transformations to transform quadratic functions into fitting situations or describing real-world contexts. So y equals, in general, or we could say f of x equals a times f of x. I guess we already don't need the f of x part. So in general, we have a times f of x minus h plus k is what we had in our warm-up activity. We had those 3 there. Technically, there's another one that you can put out in front. You can put a b in there. And that's going to stretch things horizontally. But we're going to focus on the vertical stretch and the translations, which are the horizontal and vertical changes. So just those 3 are here. So just a recap of what those do. All right, so let's get into quadratics. So if you can see on my screen here, I've got a number of different data points here. I'll scoot a little bit closer here so you can see. I've got some data points on the screen here, and I want to come up with a quadratic that best fits that data by hand. So I know we talked about last time how to do it with using technology, but I just want to kind of reiterate that idea, but also the transformations idea of how to transform quadratics to come up with a quadratic that fits this set of data points. So I have my data up here, and I can come up with the quadratic regression, like I said before, but we're gonna try to do this by hand. So y equals, and then I'm gonna use the keyboard down here. So I can start with x. The easiest form to do this, think about quadratics and transforming them with is vertex form. So I'm gonna start with a parentheses, x. Let's see, the vertex might be around, I don't know, 5 or 6. So maybe x minus 6 squared. And see, the y value would be maybe about like 9 or something, so plus 9. The problem now is it's concave up. I want it to be concave down. So I'm going to put a negative out in front to do that there. So I've shifted it. I've shifted the normal quadratic, which I can graph here just to compare, y equals x squared. So we've taken this original, this is what we call a parent function, this original function, and we've done some transformations to it to make it look like this so far. So all we've done so far is we've shifted it to the right 6, up 9, and then we made it concave down by putting the negative out in front here. Okay, but we're not done yet. We can do better than this, can't we? It looks as if we might need to open this up a little bit, or compress it vertically a little bit. So we can do that by changing the a value out in front here. So if I want to compress it vertically, I need to put a number less than 1. So maybe 0.3. Okay, that's too much. How about it's not enough actually, 0.4. Probably need to shift it to the left, so maybe it's not at 6, maybe it's at 5 or something like that. So, or maybe 5.5. Try 5.3. Okay, so that's a really good fit of our data values, and we did all that manually, just by kind of thinking through these 3 numbers here and what's going to be the best fit for that. All right, so that's kind of how we can do that, changing those 3 values with a quadratic function. I'm going to put a link in the Play Pause It and in the YouTube video here to this marble slide activity that you can try and go through. This is slide 2, and I want to work through some of this together just to show you kind of how this works. So what we want to do is we want this ball, when we hit launch over here, we want this ball to go through the stars. Okay, so if we hit launch right now, I don't think it's going to work. Yeah, it got that first star, but because our quadratic was there, it kept it from getting the rest. So what we can do is we can edit this quadratic to better fit and go through the stars. So you probably are thinking right now, you might want to negate this quadratic so that it's concave down. So I agree with you there. All right, and that might be it. That might be all that we need to do here. So let's hit launch and let's see if it works. All right, success, cool. So we were able to make one change there, and that altered the function enough to where it actually works. All right, I want to show you one more from this marble slide activity, and this is slide 4, where you've got a quadratic here, and it's more complicated because we got these 3, which we might be able to make a quadratic for, but then you got this one down here. One thing I want to point out is these curly braces here. If you want to restrict the domain of your graph, you can do an open curly brace, and then whatever the domain is, here it's x is less than 5. So we only see the graph from 5 and below. So all x values greater than 5, there's no graph. We don't see it at all, okay? So you can't edit that if you want, and change that as you go here. So because this is a full quadratic, but with the domain restricted. Okay, so let's see if we can figure this one out here real quick. We want to open things up a little bit more, not only to catch the stars, but also to catch the fall of the ball here. So maybe like, let's see, we want to stretch this or compress it vertically. So let's maybe go from 2 to being like 0.4 or something like that. So if we look at it right now, it's going to catch this one, maybe this one. Let's see what happens. got those three, but we did not get this star down here. So let's see what we might be able to do here. Let's see. Maybe if we continued this quadratic further, it would have less, forward momentum and more upward momentum, and it would maybe drop down and hit that star. So let's change this 5 as our domain restriction to maybe like 7 or something like that. So now it's going to go up a little bit higher and maybe come back down. So let's see what happens. Okay, maybe too much. So how about maybe 6? Nope, not gonna be there. Let's see. 8 would do it. There we go. Okay, so it's kind of just a matter of playing with the numbers, but also kind of thinking through like how each component changes the graph. And so we talked about transformations earlier this year, but if you continue this activity, you can actually try these transformations with a quadratic and see if you can get the stars for this marble slide activity. All right, so that was our goal for today, was to look at transformations of a quadratic and how to transform it in those 3 ways. So we have a vertical stretch or compression. So the larger the value, the more it's going to be stretched vertically. The smaller the value, it's going to be compressed down vertically. And then of course we have the horizontal shift, which is really your X value in your vertex. And then we have the vertical shift, which is the typical Y value in your vertex that we think about on the outside. So hopefully you were able to learn about the transformations of a quadratic, and we'll see you next time.